In the last part of my talk, I'll try to talk a little bit about things for which I don't really have an answer, or I maybe only have an inkling of an answer. But certainly, these are the problems that I'm trying to think about these days. And I feel like these are the problems that are going to be big challenges for privacy and privacy technologies in the coming years. And I think what they have in common is this issue that we're going to be living in a world where we have untrusted code with significant degree of access to sensitive personal information. And this Airavat framework that I described in the previous lecture, it was an early attempt to do this kind of, using untrusted code to data mine sensitive data on a large scale. And I don't know if, it was an early attempt. So some things worked, some things didn't. So, but I'm thinking about problems a little bit differently now. So, and this is what I'm working on these days. So I've been writing various papers about this over the past few years. As you can see, the titles have something in common. I already talked a little bit about Memento and how it could, statistics of system outputs could be used for adversarial inference. Eternal Sunshine of the Spotless Machine is another paper that we published last year that I will not be talking about, even though I kind of like it a lot, which looks at yet another aspect of privacy. But for the remainder of this hour, I will be talking about a scanner darkly, and I will be talking about piBox that I briefly mentioned in the past, in the previous lecture. So both piBox and a scanner darkly, so those are two very recent papers, both came out in 2013, and they talk about different aspects of the same general problem, maybe not a problem, it's just an observation about the world, how it is today, the world of software. It's all about apps now. Okay? So the computing infrastructure these days is changing a lot, and both on mobile platforms, in browsers, on desktops, and even in emerging domains like perceptual computing, we seem to be entering a world where software is developed and delivered as apps. So these are programs that are that are developed by lots of different third parties. You typically get them from an app store. They run on the platform, and they provide all sorts of useful services to you. But bottom line here is that we really entering a world where we cannot trust the provenance of software. So there are so many developers, so many apps, so many different programs that are going to be running on all computing platforms we have, that we just cannot rely anymore on the traditional model where you trust the author of the software, like it comes from Microsoft, I run it, I trust it. So you don't know where it comes from. So the problem of how to develop privacy-preserving programs, it might not even be all that meaningful anymore, or maybe it's becoming much harder than it used to be. Instead, you really need to be thinking in terms of platforms. So how do you develop platforms that protect your privacy and privacy of your data, even when an untrusted application, an untrusted app is executing on your platform? So, and that's what I'm thinking about these days. And I feel like that's the real area, that's where the action is going to be for the next few years, until we find some kind of solution to this, is how do we design and implement app platforms that accept untrusted code and still provide some kind of privacy guarantees to users whose data these apps operate on. There are several principles, and these are not technical principles, if you will. These are kind of philosophical principles about system design and how software should be built and so on that I feel are important. And like I said, I mean, this is a work in progress. These are just some thoughts that come to mind after working in this area for quite a few years. So let me talk about a few of these and see if they make sense. So one aspect that I feel is very important, and I already said it and I'm going to say it again, is that somehow I feel we need to move away from trying to figure out if a particular program or a particular piece of software is privacy preserving to enforcing privacy at the platform level. Okay? So whether the platform is something like an app store, where the platform is a mobile operating system, what have you, it's going to be important to make sure that it's the platform that's enforcing the privacy, that you're not trusting individual apps, because we're never going to be in a position to do deep enough analysis of these untrusted apps to ensure that they do privacy. So move the responsibility for enforcing privacy from individual apps to the platform. In order to do this effectively, it's important that platforms provide usable system abstractions. That is, it should be easy to build useful apps. Privacy enforcement is never going to be a priority for people who develop apps. If it gets in the way, people will find ways around it. So it's important that whatever facilities are being provided by the App Store or the operating system or whatever platform you have, they actually support in a natural way what applications are trying to do functionally, because we know that functionality is always going to take precedence over privacy and security. That's just how the world works. So it's important to take that into account. It is also very important to support apps' business models and don't mess with how apps make money. If we're talking about free apps that are advertising supported, you better provide decent support for whatever advertising functionalities apps rely on, because if not, you're kind of taking their rice bowl away from them, and this means that probably they're going to find a way around your protections. So it's important to keep this in mind and focus not just on purely technological issues when designing and implementing this platform, but also understanding how they fit into the whole ecosystem of apps and advertisers and trackers and third-party providers and so on. And finally, it's important to inform users about what's going on, because as you'll see, there are a lot of emerging privacy issues these days and also in the future for which it is not clear that we're going to have a good technological solution. So we can solve some aspects of it, but by and large, some of these issues seem just too difficult for technology, which means that if technology is not going to help, you will have to rely on the user somehow, and you will have to inform the user and let the user to be the ultimate judge of what constitutes a privacy violation and so on. There is a role for the legal system too, and for regulations, for things like punishing misuse of data and so on, but certainly informing the user is an important part of it. So let me now talk about how these principles are embodied in the two experimental platforms that I've been involved in designing and implementing. And like I said, this is very new work. Both of these papers came earlier this year, one in NSDI, the other in Auckland. And so this is very much a work in progress, and who knows, maybe I'll go through the same experiences with Airavat. That is, 3 years later, I'll be able to talk about their limitations and so on. But for now, I'm pretty psyched about how it's working out. At least it helps me clarify my own thinking about the problem. So piBox is a platform for apps that we developed. And I mean, you could think of them as mobile apps, but it's not really limited to mobile apps. You could do, for example, web apps on something like Chrome apps in a very similar way. So, and this tries to do exactly what I talked about, how to move the responsibility for privacy enforcement from an individual app to the platform. And it's a fairly complex system. There are lots of moving parts, so I'll try to explain it the best I can, even without relying on slides too much. But roughly the idea is that you run every app instance inside a sandbox. So the platform provides a sandbox that isolates app instances from each other, and furthermore, isolates them from even their own publisher so that they cannot exfiltrate sensitive information, while providing several channels that are controlled by the platform itself that allow this kind of control exchange of information where we can provide certain privacy guarantees. Let me start with a simple one. So content, so there are 5 of them. I think they're all 5 on the slides. There is the content store, sharing channel, inbox, private vault, and aggregate channel. So what are these all about? So content store is a very simple thing. In many apps, they're just designed to show content to the user. Think about a news reading app or some kind of media consumption app. And content store is a simple facility that the platform provides that works like this. The publisher or developer of an application can only write into it, and applications can only read from it. And the way these sandboxes are constructed is that the sandbox spans the device in the cloud. So there is a piece of the sandbox that lives, for example, on the mobile phone or in the browser. And there is a piece of a sandbox that lives on the cloud backend. So intuitively, you can think of it like this. Suppose I have a movie watching app. App publisher puts movies into some big cloud storage, and it can only write, cannot read. And then app instances, all the thousands of apps running on people's mobile devices, access movies in that cloud storage and show them to the user. Obviously, this is a very safe way of passing information in because there is no channel back. There is no way to exfiltrate any information because this mechanism, there will be other mechanisms, but this mechanism basically doesn't provide for the application to inform the developer, for example, which movies the user watched. Another thing it could be used for is showing advertising. So ads are put into the content store, and then the application, when it needs to show ads to the user, reads them from the content store and shows ads. So that's very nice, although as soon as I mention ads, you should be seeing certain limitations of this mechanism. So anybody wants to, if we had this mechanism alone, this would totally break the existing kind of advertising ecosystem. Why?
You cannot do any predictive advertising.
You cannot do, well, you actually can if the algorithm for deciding which ad to show is in the app instance. Then it decides based on the user profile which ad to show, but the information never flows out. So you can do, in that sense, you can do predictive advertising. However, I mean, you're not that far from the truth because, for example, there are many ways of showing ads now that are totally incompatible with this. For example, a very common way to show ads now is via real-time auctions, where I see user's profile, and then I put it outside and put it out to the highest bidder who is willing to pay me 10 cents to show an ad to this very valuable user who is looking to make an expensive purchase tomorrow. Okay, 10 cents. Do I hear 15 cents? No, seriously, these auctions are happening all the time. This would not work here. Exactly. You cannot bill, because you don't know how many times the ad was shown. You do not know. You're absolutely right. So it's kind of nice in theory, but this mechanism alone, helpful as it is, will not solve that problem. But it's good to have it. Then there is another mechanism known as a private vault. So this is a storage that only an app instance has access to. So neither application, it can read and write into it, but other app instances cannot access it. For example, users' history could be stored in there, or maybe we have a password management app that stores users' password in it, and that's sort of completely private little box, which other apps cannot read or write. Then we have a facility called Inbox. This is a structured way for apps to communicate with each other. And the way this information flows to the inbox is through something called sharing channel. And this is a pretty dangerous facility because it allows one app to send information to another app. And unfortunately, in the general case, we cannot even tell which information is being sent. So think of a typical app which, I don't know, you take a photo and you share it with all your buddies in a social network. That's a very natural kind of functionality. But the reason you cannot provide meaningful privacy guarantees about the content that is being sent is because, it's a picture. You don't know, like a malicious app could be stenographically encoding all kinds of information in the picture, and we really have no way of preventing that from happening. So in this case, our protections are somewhat limited. We do ensure that the identity of the recipient is confirmed by the user. So even though we don't know what information flows out, we control where it flows. And finally, there is a fifth channel here that we call the Aggregate Channel, which is a way for app instances to reveal certain statistics about collective behavior of app instances, such as top most viewed articles, how many times ads were shown, usage statistics, bugs, crashes, and so on, basically to flow some information back to the developer. And this is where the biggest privacy risk lies, because that would be in a normal app ecosystem where apps just get unlimited access to users' personal data and can send it anywhere. That's how personal information would flow out. It would capture everything you do and then send it back to mothership where it's going to be sold and shared and abused to the end of days. So it's very important to design this channel correctly, because that's the only way the information kind of leaves our platform and goes back to the developer. Okay? So that's kind of where most of the privacy action happens. And so this is Aggregate Channel provides a mechanism for the app publisher to gather data on collective behavior of app instances. And again, there is this pattern here, is that somehow it's okay to reveal information in the aggregate, meaning, what causes most crashes, which ads are being shown most often, how often, and so on, but not information about individuals. So what do you feel would be an appropriate mechanism for doing this? So if you want to reveal some privacy-preserving statistics, some privacy-preserving aspects of aggregate behavior without revealing individual inputs into this aggregates. So what seems like a good mechanism? Well, there aren't all that many mechanisms that I have talked about. So differential privacy. All right. OK, very good. How about differential privacy? So differential privacy is a good answer. Well, I don't know. Good answer, bad answer. It's the only answer, right? It's the only thing we have for privacy-preserving publication of statistical aggregates. But here there is a little twist. Okay, so the problem is that in this system, if you look at kind of real-world app behavior, there are lots of counters. And basically, if the amount of noise you add, if you just use straight differential privacy Laplacian mechanism that I described an hour ago, straight out of the box, for infrequently updated counters, you end up adding a lot of noise, and effectively you're returning values with high relative error. So basic differential privacy is going to produce very noisy answers. Fortunately, when designing this system, we stumbled upon a stock paper by differential privacy people on something known as differential privacy under continual observation, which is a very nice tweak on differential privacy, where not just the value you're releasing is differentially private, but even the timing of the release is differentially private. So intuitively, you can think of it, you only release counters when the true value is high enough so that the noise you're adding is relatively small relative to that value. If you don't have enough to release, then you don't release it. So effectively, you modulate not just the value you're releasing, but when you release it to ensure that your relative error stays relatively low. So this is a very nice mechanism, very efficient to implement. And it's always pleasing for me as a more systems person to be able to use an algorithm from a stock paper kind of in a systems paper. So this is a little twist, which is very nice. And as far as I know, this is the first actual implementation and kind of real-world usage of differential privacy under continual observation. So there is a little tweak there. But at the end of the day, it's the same basic differential privacy, which has the same issues. In order to be able to use it, app developer has to specify parameters like the value of epsilon, the trade-off between noise and privacy, things like privacy budgets. So it's a little tricky to do it in a usable way. So it's still an ongoing struggle. Yeah.
In this case, the platform is the one aggregating the data? The one that
the platform is aggregating the data and enforcing privacy and sending results. Yeah. So it's all privacy protection is done at the platform level. So I mean, the platform is providing these channels, like aggregate channels and sandboxes and so on. So yeah.
It has to actually hold the database. The platform is not the one that has to hold all the data from all the apps.
Right. But it's done. I mean, we engineer it so that the abstraction presented to the app just put the data into this channel and then it'll magically appear on the other end with some noise added. So that's what I mean by usable abstraction. So all this complexity is hidden in the platform and invisible to the app developer. As far as the app developer is concerned, just make this function call, and then the app instance makes the function call. Sometime later, the app owner sees a differentially private result assembled from multiple apps. So the piping is invisible to the app. So that's providing usable abstractions. And another thing we provide is trying to inform the user, because as we all know, users have a hard time making privacy judgments and deciding when it's okay or not okay to accept something, like you install a typical app like an Android, it asks us, this app has access to like some laundry list of things. What are you going to do? Like, yes. I mean, is there any other answer? So that doesn't seem like the right privacy model. So what we try to do here is to color code apps based on their functionality in terms of channels they use. So basically, we look at what facilities provided by the platform they use. So if it uses only private vault, content storage, and inboxes, we know that this app is sort of safe by construction because there is no way for it to send information anywhere else. So basically, this means that all the flows are one way. They go into the app instance, but they never go out of the app instance. And those are green. I mean, there cannot be any privacy risks, assuming our platform is implemented correctly. Famous last words, but yeah.
Back to basics for a second. If I understand correctly, you're assuming that the platform is trusted.
Yes.
The application is not trusted.
Right.
But somehow I do trust that it is running on that platform and not elsewhere.
Right.
And the protection is protecting. Now the data is on the platform, my data.
Right.
The application has no other place to use it, hide it.
That's right.
And you're protecting my data from abuse, my privacy from abuse by the application.
That's correct.
And also one application from abuse by another one, or that's not really relevant because
they can only communicate through the channels provided by the platform.
Okay.
But we do assume that these apps run on our platform. Of course, yeah. And we provide this limited number of kind of things they can use on the platform. And I mean, we know that it's feasible because as part of doing this, we ported some application to the platform and we showed that they can run. And we can show that, we showed that we can do pretty sophisticated functionality just with the things that our platform provides. But yes, it has to run on our platform.
How do you guarantee that when I see an app and install it, it is really running on your trusted platform and not running on some other?
This is somewhat orthogonal to the problem we're trying to solve, but it's the same way you guarantee. How do you know that an app on your iPhone comes from Apple App Store? It's the same problem, and you have to solve it. It's an important problem, but it's orthogonal to the privacy problem that I'm trying to solve here. Yeah?
You're assuming that any such application that has only inputs cannot signal in any way to someone else. But you also mentioned that your application collects aggregated data about bugs and crashes. I would crash my application intentionally every once in a while.
Sure.
Even though I'm not doing anything with the aggregated
data. Yeah. But information about crashes flows out only via aggregate channel. So it'll only get reported if the same crash, if like multiple instances crashed in the same way, and then in a differentially private way, information about that crash will flow out. Yeah. It's actually, it's somewhat non-trivial. It took actually like another paper to implement that functionality correctly. That's a very good point, because there is always the possibility of these covert channels or side channels. And if you're not careful, then that becomes like huge bandwidth. I'm just going to crash in different ways depending on what I want to signal out. So that's totally right. Mm-hmm.
Again, you're assuming that the app developer somehow communicated to you that he aggregates data and sends it.
Aggregation
can send it once in a while and aggregate the statistical data over time for analysis outside.
Aggregation is provided by the platform, not by the app developer.
Yes, but you talked about applications that don't store the data that they use, which means whenever you open the app, you use it.
No, they can store it. They can store
certain data, it doesn't preserve it.
They can store it.
Others that do this, that can actually preserve it, they don't have to communicate to you, the user, that, hey, I'm aggregating your data over time and your usage over time, and then I'm going to communicate it.
Yeah, that's fine. We take care of this, I believe. I mean, they can store data across invocations. And when the data flows out, it has to go through the aggregate channel we provide, which adds noise to it and so on.
What happens if it doesn't want to go through your pre-approved aggregated channel and just go through a standard channel?
The platform is designed in a way that it has no way of doing this. The only way, that's how the sandbox is designed. Okay. The only way out of the sandbox is through this function call that goes through our aggregate channel.
So by default, it goes through the aggregate channel, and then it says, okay, I have no data, or it's sanitized or whatever, it doesn't have any private data, I can let it through.
No, it doesn't let anything through. I mean, it doesn't let anything out unless it's via aggregate channel. There is no notion I'm going to send out sanitized data. There is only one way out, through the aggregate channel.
Okay.
Yeah. It's important, because otherwise it becomes a problem. I mean, you're right on the money there. It's very important. Yeah.
Okay. Thanks.
So I'm missing something. Let's say there's an app that plays some game, and you need to update the high score table in some server. How can you do that?
Well, when okay, so okay, so you cannot do it like in the raw form, okay, because this is individual data, okay? The high score of a particular user is an individual data, but you can release it in a privacy-preserving fashion, right? If you're willing to live with noisy high scores, high score is between 4,000 and 5,000. Yeah, you can do it. I mean, it's not ideal, but otherwise, I'm going to be exfiltrating personal information through high score, so yeah.
There are lots of applications that simply won't be able to work in this kind of configuration. What about chatting or?
Exactly. No, you're absolutely right. So chatting will work because it'll use like sharing channel, but there will be a different color coding for it. So let me just finish this slide, and maybe this will answer your question to some extent. So if you have an application where information only goes in, and that's a subset of application, that's not all of them, but if it only goes in, then we'll color code it as green. So because there is no privacy risk, because if the platform is correct, it only flows in. If it uses an aggregate channel, that is, if application instances don't talk to each other, but they can send some aggregated differentially private information back to the mothership, we'll color them as yellow. And finally, if it uses sharing channel, which is things like chatting, then we'll color code it as red, precisely for the reason is that with a sharing channel, we cannot enforce any privacy. We don't know what information flows from one instance to another. So that could involve exfiltration of information. The only thing we can do in this case is to confirm the identity of the recipient. And we can still guarantee that for a chatting application, there is no flow back to the developer. So whatever information flows, it flows from one instance to another. But for example, the contents of chats never go out to the developer. Okay?
Okay, what about an application like Waze that needs to know your location in order to calculate an optimal route.
All right.
There are lots of applications where the server needs information from you, or else it just won't work.
Okay, so definitely any application that has to provide personalized service to you based on your personal information will not work on this platform. Okay, so I don't know, like you know, I can think of lots of examples where it needs to do things for you with server's assistance based on specifically what you're doing there, in which case such an application is fundamentally not privacy preserving. Okay, I mean, it's like you cannot even hope for privacy because you're exchanging your personal information for some service. I'm a little reluctant to say that Waze is such an application. I don't know. I need to think about it. If there is some clever way of doing it so that some routing advice provided to you is not, I don't know. Sorry. Like for this particular app, I need to think this through. So for every app, unfortunately, porting it to this requires some process of thinking, how do I engineer it using these 5 channels? All I can tell you is that my sense is that a lot of applications could be done in this way. Definitely not all of them, and the reason not all of them is that some functionalities just cannot be made privacy preserving, and that's that. Okay, that's just, you know, you just know right away, you're informed. You're giving up your privacy by using this application, and that's a bargain that you ought to be comfortable with. I'd like to look at the glass as being half full here, is that there is a huge number of applications where you don't have to deal with this bargain. Whereas now the world is such as that an app has access to everything, or everything it asks for, whether it uses it or not, and everybody says yes, and then even apps who don't need information end up exfiltrating it. So, sorry, that's kind of an elaborate answer there. Okay, so let me now talk for the remaining half an hour about a different scenario, but it's different and yet similar. Because again, it deals with untrusted apps operating on sensitive personal data. Well, I'm told that the future of computing is perception. So, and there are lots of terms for it: context-aware computing, ubiquitous computing, perceptual computing, context-aware, natural user interfaces. Well, I don't think there is a definition for it, but what it boils down to is that there is a whole class of emerging computing platforms that interact with their users in non-conventional ways. That is not just by mouse and keyboard. They interact with their users by looking at them and by looking at their surroundings. So these are obviously things like Google Glass, okay, and applications running on it. As you know, it has an API. These are robot applications, which actually are now running. There are app stores for robots, and these things can look around them, and they can even move around. So I hope you believe me that a robot that can move around and that's running untrusted code presents and has network connectivity, presents interesting privacy challenges. Things like natural user interfaces, you know, Microsoft is very big on this. They have this Kinect, which interacts with the users through gestures. There are lots of augmented reality apps, both on gaming devices and phones and so on. So, and this is a new era of computing that's dawning upon us that is going to present really, really interesting privacy issues. Because these things, they're watching you, okay? Some of them 24/7. I mean, this is not just collecting data, you know, kind of in an old-fashioned way. You know, you have some files on your hard drive. I mean, they see a lot. I mean, think about these things. I mean, they're constantly watching. They're watching their users. They're watching what's happening around them. This is very fine-grained data. They capture not only their users, but the environment they're in, the rooms, street scenes, who is standing behind the user, who else is in the room, and so on. So that's a little interesting from a privacy perspective. What's even more interesting is that they're increasingly running untrusted code. So this App Store model that has proved so popular on mobile devices is totally moving into the realm of perceptual computing. So there are now things like robot app stores. You know, you can get all sorts of coolest app for your, you know, Roomba or what have you, and things with cameras and so on. There are whole libraries for computer vision that app developers use to write applications that have access to camera feeds, augmented reality apps, and so on. And again, this combination. So this is an interesting combination. So first of all, you have untrusted code, and second, you have really detailed information about environment. This is much more sensitive data than anything I've talked about so far. These are not just kind of discrete things like movie ratings or purchases and so on. This is everything. This is your home. These are street scenes. Everybody, you know, people around you. So very fine-grained information where it's hard to tell. You know, what's sensitive, what's not sensitive, and so on. And obviously, in these apps, we're going to face a bunch of privacy risks. So the most basic one is same as in mobile phones, but even more serious here, and that's over-collection of data. That is, you have some app, and all it needs to do is recognize your face, or you have some app running on a robot dog, and all the dog needs to do is track some ball. But the only way to do this is to run the camera 24/7 and to be watching what's happening. So it just over-collects, you know, the entire camera feed of your room, even though its only purpose is to recognize a couple of gestures. So that's the threat. Even that threat is largely unsolved today. But of course, there are much more sophisticated threats, like sensitive items that end up in the camera's field of vision. For example, it can read credit card numbers. I mean, this camera is a pretty high resolution. It can read license plates. It can read contents of computer monitors. Then this information could be aggregated over time. So you can do tracking and surveillance and find certain patterns. Even more information leaks out that way. And the hardest one is what I'll call semantic inference. And that's, I just don't know how to deal with this, and I'm not even going to promise you a solution in this area. Because think about it. Like, if a camera is watching a room, then even apart from it being able to see concrete things like, you know, credit card numbers and recognize faces and so on, even if you eliminate all that information, there is still a ton of very sensitive information that could be inferred just from the context. So you can see, you know, there was one face in the room, now there are two faces. Even if you don't see the faces themselves, the fact that the faces got close together, certain gestures, you know, you can see like a skeleton outline picking its nose, you know, like there is just so much context there, and you can infer so much about what's happening, even if you don't have access to fine-grained information in the field of vision. You don't have access to numbers, you don't have access to faces. Just the skeletons, the movements, the patterns, how many people were in the room. Once you start to think about it, you realize there is just an infinite number of possibly sensitive things that could be inferred by observing the environment. And this is really going to present a serious challenge for privacy technologists in this space, and I'm not even convinced there is a good technological solution to this. And I can tell you right away what the non-solutions are. So kind of the good old-fashioned access control, you know, blocking access to perceptual inputs, they're just a non-starter here, okay? Because the whole purpose of these apps is to analyze and use information about their environment. If you download an app for your robot and it asks you, this thing wants to access your camera, yes or no? That's a ridiculous question. Of course, the answer is yes. That's why you downloaded it, right? Like, it's access to information about its environment is the main part of its functionality. It doesn't work otherwise. So you somehow have to deal with the fact that it does. The question is, can you restrict this access in some way? Can you provide a more structured access versus, all right, you need a camera, fine. Here is the camera feed. Do whatever you want. So you need to find like a different abstraction there. Anonymizing collected data, that's another one. You know, I don't know. How do you anonymize a video feed of a room? I mean, that's, I don't know. And differential privacy, you know, attractive as it is, yeah, well, you know, it takes a better man than me trying to apply differential privacy to perceptual information from the environment. So just in the remaining few minutes, I'm going to talk briefly about this paper that we did earlier this year called A Scanner Darkly. So this is really like a first kind of baby step in this direction towards privacy for perceptual applications. So this was mostly done by Suman Jana, my PhD student whom I mentioned, but yeah, also working with Arvind and myself, assisting him. So what we have there is a system called Darkly. It's a domain and data specific system for protecting some aspects of user privacy from perceptual apps. And by the way, this is pretty unusual. So most privacy systems I've talked about so far, they tend to be generic. You know, any data mining computation, any app, any platform. This is really very specific to computer vision applications. That's what gives us some leverage on this problem. To be portable, so that it runs on, you know, robots and mobile phones and so on, it's integrated with OpenCV, which is a popular computer vision library. And it's designed to be almost transparent to existing software. So many existing applications, good applications that actually don't do anything bad, they tend to run on it without any modification, which is very nice. And this system provides sort of several levels of privacy defense. And it doesn't, of course, solve all the problems I talked about. It's mainly designed to deal with the problem of over-collecting data. But it does provide, but for that problem, it provides multiple levels of defense, such as access control, certain algorithmic privacy transforms that I'm going to show you. And as always, if technology doesn't work, user audit is the last line of defense. So it provides some way for the user to understand what is being shown to the app and enables the user to decide for himself or herself if they are comfortable with that information being shared. So our main leverage point in trying to design this privacy technology for perceptual apps is to exploit the fact that very few perceptual apps work directly with video of their surroundings, okay? And the reason is very simple, because computer vision is hard, okay? It's a very hard problem. So no app writer wants to spend their time, you know, like segmenting the visual scene into individual objects, analyzing objects, computing their movements, and so on. So they don't want to do this because it's very hard, and there has been a lot of research on this and so on. And that's why they tend to use computer vision libraries like OpenCV, which is very nice for us because this computer vision library sort of operates at the right level of abstraction for us to try to provide some privacy layer between the app and the computer vision library. So that's exactly where we're going to stick this privacy protection layer in a way that the library API remains unchanged. So as long as the application is not accessing raw data, and we find that most of them don't because they don't know what to do with it, they don't know what to do with the pixels, it only makes calls to computer vision library through a structured API, which is going to change what these API functions return in a way that preserves privacy to some extent and prevents the application from getting more than it needs. So it will never get access to raw pixels, but instead it's going to get something that will help it achieve its objectives, such as, you know, computing some features of the image and so on and so forth. So let me emphasize this importance of operating at the right level of abstraction. As you really want to do privacy protection, it's very hard to do privacy protection at the level of individual pixels and so on. So you need to find the place where objects are sort of kind of low enough level so that it's flexible enough to support different applications functionality, and high enough level so that you can reason about what it means for this object to be privacy preserving or not. The way it's architected is it tries to take advantage of kind of standard OS user isolation that I talked about at some length. So it basically interposes a Darkly process between the application and the computer vision library. And there is part of it that runs in the application that could be untrusted, and there is the part that runs in the operating system. And the idea here is that in order for this to work, you have to trust input sensors, you have to trust OS and hardware. In particular, it's very important to be working in a platform where the application cannot access input sensors, such as cameras, by any means other than via the library. As long as that's true, we sort of interpose on the library access to provide our defense. So the model here is that everything is trusted except the application. In particular, the platform is trusted. It's a very similar model to piBox, except in a different setting. Okay, so and like I said, we do multiple defenses there, multiple layers of defense. Access control is the most basic one. So OpenCV, it passes around these pointers to pixels. So it calls one library function, gets a pointer to some pixels, and then passes it to another library function. That's the standard pattern. And one trick we do, we replace these pointers with what we call opaque references. And this is a nice trick. To an application, it looks exactly like a pointer. So the application doesn't even notice that it's been faked and given a fake pointer, as long as it doesn't try to dereference it. But here is the thing. Good applications, they never dereference pointers to raw pixels. All they do, it gets it from one library function, passes it to another library function. So this is like a magic pointer that an application cannot dereference itself, but it can pass it to another function. And this ensures that trusted library functions always have access to raw image data without any loss of fidelity. No problems there. But good applications do not, they don't even notice anything because they never dereference it. But if a bad application tried to dereference a pointer and get at the raw pixels, it wouldn't get anything. So that's one kind of nice trick done in a way that basically the application doesn't even notice. Of course, that's not enough because not all functionalities can be implemented just by chaining library functions together. In some cases, an application does need to look at certain features of the image, like it needs to do contour detection and so on. And for those functions, we use privacy transforms, which are task specific. So we have a small library of things that do different things depending on the task. For example, here is a transform. So these are different levels of transformation. So there is actually a special window that controls it with a slider. Like any good slider, it goes from 0 to 11. It controls how much transformation is applied to the image. And you can see, so this is known, this transform is the sketching transform. So basically, it only retains coarse features of the image and not the fine-grained features. And you can see this is the original image, and you can read it pretty well. And as you apply more and more of the sketching transform, like at higher level of transformations, maybe you can see that this is a credit card, but you don't see the number, but you can see which credit card, like Visa or MasterCard, and then you almost see nothing. Okay, so this is, but again, this is task specific. This is where we really exploit this domain specificity of it, and we exploit OpenCV. So this is a little bit ad hoc. I'd like to have a better answer there, but that's the best one I've got. And finally, there is the user audit, meaning that the user can actually see on a special console window what is it that the application is getting. So the user can say, oh, that looks like too much, so let me adjust the knob or move the slider so that the application is getting less. Fortunately, we discovered that most existing applications, they have no problem working with this transformed images or transformed features, because it turns out that for the most part, the kind of things they do, they detect movement, they track objects from place to place, but they don't really need all that much. Even if this is somewhat imprecise or even all low-level features are lost, they can still do their job. And our system actually provides many more facilities. There is like trusted storage that it can use. There are like kind of various bells and whistles mainly designed to support existing applications. That said, look, it's a first step, okay? Mainly designed to deal with kind of blatant data over collection, which is, I am a surveillance app. I need to detect movement, and therefore I'm going to record your room 24/7 and send that video feed God knows where, those kinds of things. Or, like QR code recognizer that kind of records everything in the room in the process of recording QR code. So this is just to deal with over collection. But in this space, there are lots of unsolved problems, lots of issues that our system doesn't solve yet, and that I'm thinking about, but it's not like I have tremendous solutions at this point. I already mentioned semantic inference as being a huge challenge. So even with all these privacy transforms and information suppressed and opaque references, still An application could be observing gestures in the room and inferring things, proximity of faces and bodies, movement patterns, kind of high-level information that is very hard to eliminate entirely without kind of completely destroying what application is all about. Coming up with good metrics for privacy transforms is an interesting challenge because privacy transforms, well, I mean, clearly they eliminate a lot of information from the image, but in what sense, it's a little hard to pin down in what sense they're privacy preserving. What exactly is the definition of privacy that we have satisfied by applying a transformation that removed kind of all fine-grained contours from the image and only left coarse contours. So we don't have good metrics, don't have good definitions, and in general, what it means to preserve privacy in perceptual data is an open problem. So far, we have focused on kind of very basic computer vision tasks as supported by the library, but more sophisticated applications could be using computer vision in much more sophisticated ways. In particular, they could be using very complex object recognizers that are based on sophisticated models and so on. And we do not, at least at this stage of this work, we do not have a tremendous answer how to apply privacy transforms to those or what those privacy transfers might be. We have some ideas, using some machine learning to help with this. Another idea is, for example, if you see a face, then maybe you can have like sort of a dictionary of standard faces, and then you map that face onto a representative from the dictionary that's closest to that face. And then instead of the real face, you kind of see a standard face that's close to the real face. Could still be leaking semantic information because you can be inferring things like emotion and race and whatnot. But anyway, we have some ideas, but so far haven't solved it. And of course, usability of these systems is a huge issue because we don't know. In general, perceptual computing is kind of very young as a field. And as far as privacy is concerned, what are the right interfaces, how to present this information to the user, is user equipped to make decisions about privacy transforms? Maybe this is even misleading. Maybe once the user sees some blobs, they think that, oh boy, I cannot recognize anything here, therefore it's privacy preserving. But in reality, a lot of information could be inferred from it. So sometimes giving the user the ability to say yes or no and presenting this information to the user could even confuse the user or trick him into making bad decisions. So anyway, so I don't hold it against me that there are all these unsolved problems. This is really an area where privacy is very important and will be increasingly important in the coming years. So I hope people will do lots of research here. And let me finish by revisiting again these principles for designing privacy technologies. This is not a comprehensive list, but to the extent there is a takeaway message for the designers and implementers of privacy technologies from this part of the talk. This message is it. So I feel it's important to be enforcing privacy at the platform level, and especially for future platforms, both for apps, kind of generic apps, and for perceptual apps, and whatever have you, pretty much medical apps, I don't know, any kind of software working with sensitive information. We need to move from enforcing it at the software level to enforcing it at the platform level, at the same time providing abstractions that people can use to write useful programs and to achieve their functional needs. So that's important. Supporting apps' business models, things like advertising, whichever way they monetize, that's important. Of course, if their monetization model is like third-party trackers, that is, I'm going to track people from site to site and then sell that information to the highest bidder so that they can show scammy ads, yeah, well, you aren't going to be supporting that kind of model. But, something has to give there. But as long as there are kind of legitimate business models, it would be nice to support them. And certainly support for advertising and targeted advertising and advertising auctions is important there. And informing users. So it's not clear to me that all of these issues can be solved with technology, especially higher level issues. Higher level inference might not be. And in general, indirect inference, as I tried to argue earlier today, is a tough challenge, and there are lots of clever ways information could be inferred. And so you can inform users about it and let them take the risk or not take the risk. Another possibility is to rely on laws and regulations. It's not that we have them, but we can help draft them or somehow influence the thinking of people who work on this. And there, the focus has to go away from controlling access to the data, because in many cases it's going to be very hard to prevent, to punishing data misuse. And this is really a shift, a conceptual shift. This is a different way of thinking about how data privacy should be thought about. That is, less emphasis on who can access the data, who cannot access the data, more emphasis on what they do with it. And this is yet another aspect of the same idea that I talked about several times today, which is privacy is not a property of the data. Privacy is a property of the computation. Privacy violations are related to what you do with the data. It's not just the fact that you have access to it. It's what you do with it, how it's used, what computations are performed on it. That's where the real action is. And so both from kind of a technological perspective and a regulatory perspective, it's important to focus on data users, not on the actual data structure and access to data. And I think this is all I had today. Thanks for listening.